Okay, so in this video we're going to look at the cross product of two vectors. Now in a previous section, excuse me, the cross product. All right, now when we introduced vectors, we went over different vector operations, scalar multiplication, addition, subtraction, right? Which were pretty straightforward in the sense that they were very similar to our operations of real numbers, of addition and subtraction. One thing we didn't talk about was this idea of a multiplication or division, what it meant to do that with vectors. Now, we did introduce a new operation called dot product. Right now, if you recall, the dot product between two vectors, u dotted with v, that resulted in a scalar. All right, so it wasn't like we got another vector in return, so which made it which was different in the sense of operation. We had a different type of result, right? We had the input were two vectors, right, that we operated with, and the result was a scalar, right? And then we went over what exactly the dot product was, how to calculate it. So in this video, a couple of changes here. We're going to look at 3D vectors now. The only thing that changes here is that, well, we're in the 3 dimensions, right? Previously, we're used to components having just 2, but here our vectors will have v1, v2, v3, or our vector u, which will, again, just for generalities, I'll call these u1, u2, u3, right? Where these values, v1, v2, v3, u1, u2, u3, they're all scalars, right? They're some kind of real numbers, right? Now here's an example. GeoGebra has a nice 3D grapher, right? And what you see here is what vectors would look like in 3 dimensions, right? Here, this is vector u is 5, 1, 2. Vector v is -2, 0, 1. Okay, so notice here, right there, the axes are labeled. You have x, y, and z. Z in blue right there. Okay, all right, so the third component there is just that blue axis z coming out, right? So instead of plane, right, if you think of when we're looking at a board, you can think of that as the xy plane. The z-axis would be imagine an axis coming out of the board, right, to give us the 3 dimensions. Okay, now the idea of a cross product, or the formulation of a cross product, is to find a vector that is orthogonal, right? So the cross product, its aim is an operation, aims to find an orthogonal vector for 2 vectors. Now this word orthogonal, so we're going to define u cross v. Okay. All right. So we're going to use this notation to signify the cross product, right? So we have the dot for the dot product, and now this cross to signify the dot product. Right now, again, this term orthogonal, in 2 dimensions, we say perpendicular. When we're in 3 dimensions, we use this word, or higher, we use the word orthogonal. All right, so the angle between the 2 vectors is 90, or in other words, the dot product is 0, is another way to represent that situation, right? So what this means is if I take, let's say, I call this vector. So a couple things that are different between the cross product and the dot product is the result of this is going to be a vector. So we'll say the result is a vector. So that is one major difference between the dot product and the cross product. Okay, and the way that the cross product is formulated, and I'll show the formula in a second, is that it is meant to find an orthogonal vector to both u and v. So if we were to take u dotted with w or v dotted with w, right, where w again represents the vector that results from the cross product of u and v. In this case, both of these would be 0. All right, the scalar 0, right, not the 0 vector. Okay, so now let's finally introduce our cross product. So if u is some vector, three dimensions, and v is some vector in 3 dimensions, then we'll define u cross v to be the vector defined by u2 minus v3, excuse me, u2 v times v3 minus u3 times v1, excuse me, v2, and that corresponds to our vector I hat minus u1 v3 minus u3 v1 times our vector j hat, right? Our I and j vectors that we covered in the previous module. Now, since we are dealing in 3 dimensions, right, we do have a k hat, so that would be u1 v2 minus u2 v1 k hat. All right. Or in our vector notation and not in the component form, we'd have u2 v3 minus u3 v2 and then minus u1 v3 minus u3 v1, and then u1, the last component, v2 minus u2 v1. Okay, whichever formulation you like to represent it as, unless it's asking for a specific one, it would look like that, right? Where again, the I hat is the component vector 1, 0, 0, right? J hat is the vector 0, 1, 0, right? Again, same as before, where the first was x, y, and then that third one that we add on, that'll be the z, right? And then our k hat is 0, 0, 1. Okay, so that is our cross product. In the later video, we'll look at a way to kind of a shorthand to calculate the cross product, so that it kind of eliminates trying to memorize all these quantities here, right? And it'll involve using a determinant, which we covered in the previous video. Okay, so let's look at an example. So example, let's say I want to find u cross w, and I say u cross v to be equal to, and not equal to. Find u cross v for u equal to 5, 1, 2. And then v equal to -2, 0, 1. Okay, so I look at my formula up there, U cross V, and this states, right, for our first component, U2, which is 1, and then V3, which is also 1, and then subtract from that U3, which is 2, times V2, which is 0. All right, so that's my first component. The second component is U1, which is 5, times V3, which is 1. And then, excuse me. So minus U1, which is 5, V3, which is 1. And then minus here, excuse me, U3, which is 2, times V1, which is negative 2. Okay, and then lastly, our final component here, the Z component, we have U1, which is 5, times V2, which is 0. And then U2, which is 1, times V1, which is negative 2. Okay, and performing these operations, we see we get the vector. What do we have? A 1. And let's here, watch my signs here. We have 5 plus 4, that's 9. And then there's a negative out there, so we have negative 9. And then lastly, the Z component is a positive 2. Okay. Okay, so that is our vector. Now let me put it on the graph here so we can kind of see how it's related to the other two vectors. So let's call this one vector W. So W equals vector, let's see. And what was the point? The vector 1, negative 9, 2. 1, negative 9, 2. All right. And now we could see here, let me change the color of this here. All right. That's not enough contrast there. Hold on a second. Okay, so now you can see that vector, if you take the dot product with either of those two black vectors with that blue vector, when you take the dot product between those, they get 0. So what that means is the angle in between these vectors is 90 degrees between U and W and between V and W. All right, each individual to those compared to W is an orthogonal vector. All right, so it's orthogonal to both of those. Okay, so that's how that is the dot product and the use of the dot product.